Hello everyone. Welcome to this video where we will delve into the fascinating world of the RL high pass filter, passive. In this tutorial, we will explore the inner workings of the filter using a circuit simulator, step by step. By the end of this video, you'll have a clear understanding of how the RL high pass filter operates and how its parameters affect its behavior. Let's begin by discussing the fundamental concept of a high pass filter. A high-pass filter is an electronic circuit that allows high-frequency signals to pass through while attenuating or blocking low-frequency signals. It consists of two essential components, a resistor, R, and an inductor, L, connected in series. The cutoff frequency, FC, plays a pivotal role in understanding the behavior of a high-pass filter. The cutoff frequency determines the point at which the gain of the signal is half of its peak strength or 3 decibels, dB, below its full strength. Mathematically, we can calculate the cutoff frequency using the formula FC equals R/2πL, where R represents the resistance and L represents the inductance. In our demonstration, we have a specific circuit configuration consisting of a 187 ohm resistor and a 70 mH mH inductor. These values will determine the characteristics of our high-pass filter. By adjusting the resistor and inductor values, we can modify the cutoff frequency and tailor the filter's response to suit our specific needs. Now, let's take a closer look at the circuit simulator displayed on your screen. We have set up a frequency sweep ranging from 20 Hz to 1 kHz. The sweep time is set to 100 milliseconds, and the maximum voltage is limited to 5 volts. Additionally, we have included a scope that will display the input and output signals of the high-pass filter throughout the frequency range. As we initiate the simulation, pay close attention to the scope display. At lower frequencies, you will observe that the output signal is significantly attenuated or filtered out. This occurs because the inductor exhibits high impedance to high-frequency signals, effectively bypassing them and allowing them to pass through to the output. Hence, the name high-pass filter. On the other hand, low-frequency signals encounter low impedance when passing through the inductor. As a result, they follow the path of least resistance, which leads them through the inductor. Consequently, these low-frequency signals are effectively blocked and do not reach the output. Observe how the gain of the output signal increases as the frequency exceeds the cutoff frequency. At the cutoff frequency, the gain is approximately half of its peak value, denoted by the 3 dB point on the frequency response graph. Beyond the cutoff frequency, the gain continues to increase, allowing higher frequency signals to pass through with minimal attenuation. It's worth noting that the frequency response of the high-pass filter starts at zero gain for low-frequency signals, gradually increasing as the frequency rises. The cutoff frequency marks the point where the gain is at 50% of its peak power. Beyond this point, the gain reaches its maximum strength. By manipulating the values of the resistor and inductor, we can alter the cutoff frequency of the filter, consequently affecting its frequency response characteristics. This flexibility allows us to customize the high-pass filter to meet the specific requirements of different applications. I hope this detailed explanation has shed light on the RL high-pass filter, passive, and its behavior in various frequency ranges. Feel free to experiment with different resistor and inductor values to observe how they influence the cutoff frequency and the overall frequency response of the filter. In summary, the RL high-pass filter, passive, is an essential circuit component that allows high-frequency signals to pass through while attenuating or blocking low-frequency signals. By combining a resistor and an inductor in series, the filter creates a frequency-dependent impedance that affects the signal's path. The cutoff frequency, determined by the values of the resistor and inductor, plays a vital role in the filter's behavior. It indicates the frequency at which the gain of the signal is half of its peak strength. Understanding the cutoff frequency helps us grasp the point at which the filter transitions from attenuating low frequencies to allowing high frequencies to pass through. Through the circuit simulator, we can visualize the frequency response of the high-pass filter. As the simulation progresses, pay attention to how the input and output signals change across the frequency spectrum. Notice the significant attenuation of low-frequency signals and the increasing prominence of high-frequency signals beyond the cutoff frequency. Remember that the RL high-pass filter operates based on the reactive properties of the inductor. Inductors offer high impedance to high-frequency signals and low impedance to low-frequency signals. This behavior allows high-frequency signals to follow the path of least resistance and bypass the inductor, while low-frequency signals take the inductor path and are effectively blocked. By adjusting the resistor and inductor values, you have control over the cutoff frequency and can fine-tune the filter's response to suit your specific application requirements. This flexibility makes the RL high-pass filter a versatile tool in various electronics and signal processing applications. I hope this extended explanation has provided you with a comprehensive understanding of the RL high-pass filter, passive, and its behavior. Feel free to revisit this video and experiment with different circuit parameters to deepen your knowledge. Don't forget to like and subscribe to our channel for more educational content on electronic circuits and filters. Thank you for joining me in this exploration of the RL high-pass filter, and I look forward to seeing you in the next video.